How are we doing? Ready? All right. So I guess I'll give you guys a little bit of introduction about myself. Ooh, someone spilled some kind of sweet tea over the table. So, all right. So I did my master's and my bachelor here at MSU. So I've been around this block actually for a while. I lived in the engineering building overnights a lot when I was in my undergrad. So when I was in my undergrad, I took a lot of classes here, and there was a single machine learning class. It's not really machine learning; it's artificial intelligence in general. And at the time, this class was not really on what we use today as state-of-the-art machine learning, right? This is very much propositional logic and a foundation of what makes AI. But recently, we've obviously seen a large surge of ML-related courses in our master's program, right? When I first started my master's here, there were a couple, but in recent years, we've been adding more and more courses, and all of these are related to machine learning, right? You think natural language processing, right? You think deep learning, pattern recognition. All of these are completely ML-related courses. Even in undergrad, I think we have a couple new ones, right? Anyone taking data mining, machine learning, anything like that? Show your hands. Yeah, a couple? Okay. So yeah, obviously this is the new big hype, right? It's getting more and more popular. We see chat being used quite a bit. So yeah, I wanted to actually quickly ask, how many people have used machine learning before, right? Everyone has, right? Chat, yeah, we've all done it. Okay, so how many people have used it outside of the context of chat? Well, what are some example applications? Yeah.
Image generation, AI.
Image generation, so Gen AI, right? So that's actually very close to chat, right? You give it some prompts and it generates you some kind of things, right? Yep. Classification. Okay, in what context?
Fall detection, so seeing where that head impact.
Okay, very good. Yeah, so the text classifies some kind of issue, I guess, right here. Yep. Search. Okay, expand on that.
Right, like kind of like Google.
Google. Okay, all right. I got some pretty cool examples for you after this. Perplexity. I have an idea. So I've not used it myself, but I've heard of it. So anyone else? What's the first time you guys have interacted with AI? What's your very first products? So I'll give you my example, right? My first product that I really have not thought about as AI before, but it is the Amazon Alexa, right? So it's speech recognition. When you tell it to set an alarm, actually that's what it turned out to be, right? I bought it not for the context of an alarm, but it turns out to be just an alarm for me. But when you tell it some kind of things, it will recognize your voice, right? It recognizes what you're saying, and then it turns it into a command. So there's some kind of machine learning happening behind there, right? So I guess the point of that is just to let you guys know that AI goes beyond just chat, right? Chat is kind of our forefront, the most sellable, the most obvious uses of AI right now. But AI is actually quite integrated into our life already. And what I want to do in this lecture is really to give you guys an idea of what AI is, right? What happens behind the scene. So I guess I want to start something a little bit more lighthearted. Are they sentient? What do you think? Right? If chat becomes sentient, it's smart enough to hide it from all of us. Believe it or not, yeah? Right? There was a bug in one of the advanced model a couple of months ago where when you give it a command, right, it might pick it up and then repeat it to you in your own voice. So, if you have not worked in the space or if you're not familiar with AI, that seems kind of creepy, right? That seems like kind of out of a movie where the AI kind of becomes you. But obviously, that's a bug, right? Well, what does it mean to be sentient? Do you guys have a definition, right? If I ask you, how do you classify when a machine learning algorithm becomes sentient? Right, any ideas? This is not technical, right? This is just a purely like a philosophical question. Well, what does the word sentient mean to you guys? Yeah. Okay. Okay, so you said that once it's able to make your own decision, right? Sure. Yep.
Self-aware.
Self-aware. Okay, take that one step further. What does it mean to be self-aware? Yeah. Okay, sure. So I guess I'll help you on that one. To me, self-aware is almost like you can think about yourself as a being, right? Right. You can evolve about how you think things. Yeah. Conscious. That's also kind of hard to define, isn't it, right? If I give it to you, you know it is, right? If I tell you is this animal conscious, you can say yes, right? But kind of hard, right? So is it by definition that AI can't be sentient, right? Philosophical question, right? Nothing to do with actually what happens. So a little roadmap. Again, I wanted to give you guys an intuition. At the very least, I want you to come up with this lecture of how AI kind of works, right? You have an idea of what's happening behind the scene, right? Obviously, we have a lot of classes, and there's no way I can cover everything about AI and machine learning in just a lecture and two. But hopefully, at the end of this, I can give you guys some direction of a feel of what happens behind the scene. I want to give you some examples and applications of where we're using ML at the moment, right? Is it successful, right? Are we doing a good job with it? And then finally, what can we do and what we can't do with AI? So a bit of a, I guess, preview. I'll go into this a little bit more in depth. You've seen it in medical imaging, right? Cancer cell detection. If I give you an image of an X-ray, right? Can you identify clumps of cell that might be cancer? And then you raise it to, for example, a doctor to actually look at if you think that it's cancer. Autonomous driving, right? Our Waymo vehicles, these definitely use some form of AI in them, right? Bug plant detection, someone has mentioned earlier, but here I'm exactly thinking of an app that I've used in the past where you take an image of an insect and then it'll tell you what type of insect it is, right? Pretty cool. So goes on and on. But I guess going back to the theme of intuition, let's just start with some very simple toy examples, right? So here I've got two strings of number. The first one is just 1, 2, 3, 4, and then I'm missing a number, and then it's 6 and 7, right? What goes in here? It's kind of obvious, right? With elementary school, we've learned this is 5, because that's the number that goes in between. Okay, so the second string, I have something that's a little better, right? It's 2, 4, 6, 8, not as direct, but still very obvious, right? It's 10, right? Because that goes in between the two of them. It's linear. What about this one? I got a Carly scale, sorry. So you got red, orange, yellow, lime, something goes in the middle, mint. What is it? Again, not a trick question, right? It's just green, right? Something goes in between, it's green. But why can we do this? Why is it that when I give you these things, right, your brain already automatically hardwired to be able to tell me what is missing here, right? Even if you don't know exactly the question, right? If you didn't know, you have an intuition, right? You have a sense. Yeah. Perfect. We're very good at recognizing patterns, right? This is a pattern, right? There's some relationship between this information that becomes a pattern that our brain snaps onto, right? We've learned about this in elementary school, and then this pattern kind of repeats itself throughout our entire life, right? So this is very hardwired and ingrained into us. But let's take this one step further, right? So recently, I've been trying to learn Polish, right? Just Duolingo at the very beginning, right? So here I've got a bunch of Polish translations of each of the colors. And if I ask you, what is in the question mark? All right, so unless you learned Polish before, you know Polish. This is a very hard problem, right? Because the challenge here is previously we have some kind of correlation, some pattern in this data that we can extract from, right? But if I give you something arbitrary, kind of like language, there isn't really anything that can allow us to kind of guess what comes in the middle, right? You kind of have to know the word to be able to tell you what it is. So this really is the challenge of AI, right? With machine learning, what we're able to do is we're able to extract pattern directly from a lot of data. Right? And this is going to be a recurring theme that we're going to come back to a lot in this lecture. And if there's anything that I want you to take away from this, that's really all we're doing. We're harnessing that power in AI, right? But if we're not able to find a pattern in that data, for example, in the language here, it's very hard for us to do machine learning, right? It's actually impossible, right? You just don't have that information. So what machine learning is not good at is something like this, where we just don't have that information. So the intuition here, again, as our student in the back said, is that we really are trying to learn some pattern from this data. So we are also sometimes calling these statistical machine learning, right? What exactly does that word mean to you? Stats. Are we getting triggered? I didn't pay a lot of attention in my college stat class, and it was a bad idea. It's actually pretty useful. It turns out linear algebra and stats are pretty important. So what does the word stat means? Again, not a trick question, right? Just so to me, it's yep, go for it. Analysis of data. Okay, so let's see. What is the number one thing that you think of when you think of stats? Average. Okay. What about accuracy? Is that connected? Right. Okay. So machine learning is very much close tied to accuracy, right? But if I have a 99% accurate model, What does that mean? If I give you 100 sample and I'm 99% accurate, it's bound to fail, right? 1% of the time it's going to fail. So that's why when we talk about statistical machine learning, right? And this is why, another thing that I want to drill into you guys with this lecture is that these are statistical model, which means that they have to fail, right? By definition, they are going to fail. And it doesn't matter how accurate you are, right? Because you're learning statistically, this is the best model. There is going to be some sample that will cause you to fail. But that actually turns out to be a bit of a challenge for us because as humans, we're very good at adapting into patterns, right? So if your machine learning algorithm is correct, right, 99 samples in a row, it's pretty easy to think that the 100 sample is going to be correct, right? There's no reason to believe that it's going to be wrong. If you use your phone for 100 days and it never crashes, right, it didn't break, it didn't do anything weird, you don't expect it to do something weird on the 101st day. So we have the same idea here, right? If you see a machine learning model do a very good job for a lot of inputs, right, it's very easy to become compliant and just rely on it. So if regular people use it, like doctors, right, in that cancer example that I gave you, if I show 100 examples and all of them are accurate to the doctor, right, the doctor is probably going to start trusting it. What about developers? So we kind of know about this, and hopefully by the end of this lecture, we have an intuition of what was happening, right? We're still human, right? We're still very prone to that pattern of, oh, this thing is working, so it's going to work for the future, right? It's pretty important to keep in mind that these are going to fail at some point. So definitely need to think about what do we do when the model fails, right? How do we detect if the model is going to fail? So with this slide, I guess probably a little more important thing is right now, AI, ML, and DNNs are kind of used in the same space, right? They kind of throw that around. They're synonymous, but they really are not. So this is almost like a rectangle. A square is a rectangle, right? But a rectangle is not a square situation. So at the very, very wide net, we have just artificial intelligence. This is just concerned with how can we make machine be able to learn, right? How can we imitate humans using machines? And then at one level lower, we have machine learning, right? This is how can we teach a machine how to do statistical learning kind of stuff, right? And then DNNs are kind of the current state of the art. This is the forefront of where we're using an emulation of what human brain does in order to capture the idea of machine learning, right? Be able to extract patterns directly from data. So we've talked about this a little bit now, but I want to tie it back together and explain what data really is, right? What is data? You guys have heard of this term, definitely, right? What is data? Yep. Information. Okay. Can we be a little bit more specific about that? Sure. So pieces of information, right? So you're going to have a lot of pieces of information in a big data set, right? Okay. So in today's world, right, everything is about data, right? All the companies are mining data, right? Because we can extract some kind of pattern, we can extract some information, right? We can explain some unknowns, some patterns between the users in your data. So data really drives business finances in our current world, and it allows you to tailor experiences for users, right? So Amazon is very interested in what type of searches you have done in the past, right? What kind of videos that you're interested in, what kind of stores that you visit, because then they can tailor their ads to you, right? They can sell specific products that you might be interested in. And the challenge here is computers are very good at numbers, right? Computers are not very good at pattern recognition natively, right? But they're very good at numbers, and data can be represented into number. And you think a lot of things can't be represented into numbers, but they really can, right? So an example here I like to give is if I take a walk, like a hike, right, up kind of a rural area into the woods, right? Can that be turned into data? Your intuition probably says no, right? But in practice, if I strap a camera, right, a GoPro onto my head, and I capture each frame that I walk through this wood, and I turn each of those into pixel numbers, now they're numbers, right? So that turned into data, which then we can use machine learning to process to extract some kind of pattern or discover some kind of unknown patterns that we previously have not known. So here is a general XKCD that I like to introduce with. And it says here that this is your machine learning algorithm, right? The person coming along is going to ask, oh, is this working? So the person coming along is going to ask, is this your machine learning algorithm? Yeah. So you just put in the data into this big pile of linear algebra, and then the answer comes out on the other side, right? So you have input of your data, right? And then your output is just going to be the answer. But what if the answers are wrong? Well, you just stir this pile of math around until it's right. And really, that's kind of what machine learning is, right? So we start off with some data, right? We have some model that we need to train. And in the process of training, we're really just stirring around some numbers until we get an output that kind of looks right. And the key point I want to highlight here is it kind of looks right, right? So this is statistically, the output looks right to us. But again, the model is not sentient, right? So it doesn't have the ability for us to process information the same way that our humans' brains do. Our brains have evolved over millions and billions of centuries to be able to do this stuff, right? Whereas computers so far, we're kind of at the very, very tip of how we evolved it. So here, we have three main types of machine learning algorithm that we use today. And they're kind of roughly categorized into supervised learning, which is where we have a bunch of labeled data for our output. So these are like images of cats and dogs, right? And we want to teach some kind of model to be able to recognize if an object that I gave you is a dog or a cat, right? Or is a car. In unsupervised learning, we have a lot of data, right? We have a set of data, and then we want to clump them into their own thing, right? We want to cluster the data together. We want to find relationship between these data. Here I have an example of what an unsupervised clustering example might look like. I have a bunch of data points here. I've got triangles, I've got stars, and I've got plus signs, right? So obviously, there's subgroup relationship between each of them, right? All the pluses are kind of closely related in the clump in the corner there, right? And then all your plus signs are kind of, all your stars are kind of related together in a clump. So if I use unsupervised learning, right, the idea here is to collectively put them in their own groups, right? So everything that belongs to this blue circle, for example, is going to be a plus sign, right? And then everything that belongs to this one is going to be a triangle. Now, if I give you a new data point, right? If I ask you, hypothetically, I have a new data point here, right? It's very easy for you to just tell me, well, it's very likely for that to be an orange triangle, right? Because everything else near it is an orange triangle. So that's really what clustering algorithm is trying to do in supervised learning. And then finally, we have reinforcement learning, right? Unfortunately, we're not going to be able to cover this one that much, but think of it as a video game where you teach some kind of computer how to play a game, right? Tic-tac-toe or like chess, right? You reward it when it does something good, right? If it reaches where you want it to go, you give it some points, right? And then if it crashes or if it falls off a cliff, then you can penalize it by giving it a negative reward. So in this lecture, we're mostly going to focus on supervised learning. And what we're trying to do here is, given data set, right, a bunch of data, we would like to be able to learn some kind of pattern in it. And here we are, tying right back into that idea of pattern recognition, right? Pattern in data. And when we feed it some kind of new data, the idea is it should be able to generalize it and apply it to new learned knowledge. And again, this is bolded here because I want you to know what generalized means, right? The idea here is when I give you a pre-semester test, right? So at the start of the, your class, some of your classes in the previous times, you might have gotten some kind of test, right? Maybe a practice exam. On the first day, this looks like French, right? This is a bunch of gibberish. So maybe you just pick some random circles, right? So if you pick some random circles, your accuracy is probably random guessing, right? But the idea is as you learn the material throughout the semester, your brain learns some kind of pattern, right? Your brain learns how to correlate that information. And when I give you the final exam at the end of the semester, you're able to take that knowledge that you've learned, you're able to take that pattern that you've learned and apply to new data, right? So I can give you not necessarily the exact same question, right? I can give you the same question, the same framed in the same format, but maybe I change the numbers around a little bit. But you should still be able to tell me what the answer is because you've learned exactly what to do for this given question, right? And our idea here is very similar, right? The ability to generalize is the ability to take that knowledge and apply to things that you haven't seen before, right? That are closely related to what you have learned. Any questions so far? Feel free to stop me whenever if you have questions, by the way. Okay. So traditional algorithms, right? And these are machine learning, not deep learning. These are just going to be in the subfield of machine learning. Is the idea of linear regression, linear classification, decision trees, so on. These are very simple models, right? You guys heard of linear regression before? I promise every one of you have done this at some point in your life, right? Line of best fit, right? So what we're trying to do here is I've got here a bunch of random samples, right? Some plus signs and some minus signs. And if I want to draw a line that can separate these two data points, right? This is classification, right? By the way, whether if it falls into the plus sign or the minus sign, right? I want to be able to draw some kind of line in between the data And everything that is above this line, I would say is a plus sign, right? Anything that is below this line, I would say is a minus sign. Now, this is very easy of a problem, right? But we're still not exactly accurate because the data has some noise in it, right? This minus sign and this plus sign is kind of throwing us off. So it's not giving us 100% accuracy. But for the most part, if a data point comes in, right, and it's up here, we're pretty confident that it's a plus sign, right? And if a data point is down here, it's pretty confident it's a minus sign, right? But if a minus sign comes along and it falls above this sign, you get a little bit of an error, right? But that's okay, because on average, we're doing very well, right? On average here, probably like 90% accurate, right? So that's linear classification. Regression is basically where you fit a line, you have a bunch of data points, right? And they have some kind of correlation. Maybe they fall very close to a line, right next to a line, right? And you want to draw this line. And really, this is a lot of what's machine learning is being used for today, right? I have a lot of friends that are working in New York, and they work for hedge funds and banks, and their job literally is clean up data and then put a line onto the data, and that's it, right? So in comes deep learning, right? Traditionally, we're using these algorithms for very simple data, right? If things linearly correlate, so if they look like a line, it's going to work. But in practice, data sets are different, right? It's not everything. If everything is just drawing a line, maybe we'll have flying cars by now. But unfortunately, that's not how it works, right? If I tell you to even just do a quadratic formula, right? Your line no longer works. So if I upscale this into many numbers of degrees, it's very hard for you to just be able to tell me exactly, right, what kind of line or what kind of equation you should use. So deep learning really addresses this issue, right? And how is it done? So to this, I, again, want to go back to our theme of intuition and give you an idea of how this really works at a level that you can think of as a human, right? If we consider ourselves to be a neural network. So a couple of years ago, I went to New York and I visited my friend, and he has two cats, right? This is Dino. Dino is pretty cute. This is within 10 minutes of me entering his apartment, cat is sitting in my lap. So this is my favorite one. But this is Dino sitting in a suitcase. And this is Rex, right? Rex is pretty hungry all the time. Dino is a tuxedo cat, right? And Rex is a tabby. Now, if I were to ask you, right, I give you a 5-year-old that has no idea what cats are, never seen cats in their lives, right? And I tell you to teach them, how do you identify the cat breed? How would you do it? Yeah. Tuxedos are black and white. Sorry, what was the second part? Okay, tabby has some level of colors. Okay, so coloration, pretty good. Anyone else? Tabbies have stripes. Anything else? Right. Okay. So maybe tuxedo cats are bicolored. They might have more white fur than on average what a tabby has, right? What about behaviors, right? Maybe tabbies are a little bit more stupid, right? They're a little bit more goofy. So tuxedo cats I think, tend to be a little bit more loyal, and they kind of act very high class compared to you, right? They kind of sit in a high place and look down at you. But now, if I give you another challenge, right, and I tell you to write a program that can distinguish between the two computers, or sorry, the two cats, right? Two breeds of cats. Anyone think they can do this? If I offer you a reward of $1 million to be able to implement an algorithm that can do this, right, within a week. No machine learning involved, right? It's a very hard task. Why? Why is it that a 5-year-old kid can learn this really fast, but a machine can't? And this really comes back to the idea, right? Our brains have evolved over many, many years to be able to identify patterns, because what happens when you can't identify patterns, right? What happens when a lion pulls up to you and you can't tell that it's a lion, right? You can't tell that it's aggressive or it's dangerous. You die, right? Evolution says that you're not going to survive. Computers, unfortunately, have not had this luxury, or I guess, of being able to evolve over this many years to be able to identify that pattern, right? So it's very hard for us as computer scientists to be able to code something that can distinguish between the cats, right? Even just cats and dogs, right? So here, I got a little breakdown, right? So markings on the head is something that also kind of separates the two cats. But what about cats and dogs, right? There are a lot more things that separates cats and dogs than just colorations and so on. You can do, the snouts, right? Dogs have kind of pointier, like more rounded snouts, whereas cats don't really have one, right? The ears, right? Dogs have droopy ears. Cats typically have pointy, sharp ears. And then one barks and one meows, right? Behaviors are very different, right? That dogs tend to be more outdoor, tend to be more loyal, tend to be more playful, right? Cats a little bit more sleepy and just stay inside, right? But how do we translate this exactly into a program, right? Again, this is a very hard problem, right? And if you have an idea of how to solve this without using machine learning, talk to me, we can become very rich. So the idea here is, what if we imitate what our human brain does, right? What if we take these neurons that are, how our brain works right now? Our brain is essentially a bunch of these neurons connected together. And what if we take that idea and we implement it into a program? And this is really what drives the current iteration of neural networks, right? And here I have an example of something called a neuron, or sometimes also known as a perceptron unit, where you take in a bunch of inputs. So these are input numbers, right? And then you do some mathematical operations such as multiplications and additions to them. And then you get some kind of output. Now, this idea actually has been around since probably the 1980 something, right? How did we take so long, right? Why did it take so long for us to get to where we are today with machine learning? Does anyone have an idea? There was actually an original AI boom in the 80s to try to harness this power, right? And if you put AI on your resume at the time, you're guaranteed to get a job. And then in the 1900s, if you have AI on your resume, you're guaranteed to not get a job. So what happened there? What were we lacking at the time? Yeah, computational power. Yeah, so we did not have the ability, the computational power to really harness this capability. But with the 2010s, beginning of 2020s, we actually started having GPUs, right? The gaming space brought in and commercialized GPUs. So now we have the capability and the computational power to really harness this. And I guess a little bit of background, right? I would describe what a CPU is. So CPU is the computational unit that everyone has in their laptop and computers, right? And your phones. These are kind of like a race car that can carry few people really fast, right? But a GPU is able to do a lot of computations at the same time, but not very fast. So this is kind of like a school bus, right? Being able to take a bunch of kids from one place to another one, whereas the other one is kind of like a supercar or hypercar that can just take a few people at the same time. So GPUs really enabled us to be able to harness neural networks to be able to do what we're doing today. All right, so DNNs. Where do we get the word deep come from, right? And the idea here is we're just going to stack a bunch of these neurons, right? Again, these nodes are just a single node that take in an input of numbers, a bunch of numbers, right? And this, I just showed you 3 numbers here. It could be a lot of numbers, right? It could be any number of numbers. But the idea here is we stack a bunch of these nodes together, vertically and horizontally. And that's how we get to the word deep, right? So these are deep neural networks. Has anyone seen this before? Yeah, looks kind of familiar, right? So at a high level, this is how it really works, right? So here I have a cat. So I'm going to take a picture of the cat, and each of the pixels in the picture correlates to an input neuron. So on this first layer, right, I'm going to put the first pixel here, the second pixel here, the third pixel here, and stack it so on. And the idea here is the numbers are going to propagate through this network. And at the end of it, hopefully, right, this is the pile of linear algebra that we were talking about before. At the end of this pile, hopefully we get a good output, right? Hopefully it tells me that it's a cat and not a dog. Here's another example with a car, right? If I take a picture of the road scene with a stop sign in it on top of the car, right? This is the camera unit of the car. And then you take each pixel of this stop sign and you map it to one of these neurons. These values then propagate through this neural network. And notice some of these might not be active, and that's OK, right? And you get to this, hopefully it will be able to classify that it's 93% confident, or 93% of the features of the image belongs to that of a stop sign, right? But again, you notice here that these probabilities is an 80% confidence, right? So that means that there's 20% of the time that this might be a bird, right? OK, so to be able to visualize this a little bit, I want to start off with something called the MNIST data set, which is a handwritten data set. So if I write down a bunch of numbers and then I scan them, can I use a neural network to tell me what kind of numbers is in it? This example kind of is very helpful for me, at least, to be able to visualize how the numbers are really being used, right? So here we have an actual number of the 5, but you notice a bunch of numbers are in each of these grids, right? If you think of each grid here as a pixel, right? and black pixels are negative 0.4, and the brighter they are, the higher the number, right? Now we can see how the numbers have relationship, right? So if I draw the 5s in this specific patterns, there's a relationship in this number. So the idea here is we take this number, and then we feed it through this neural network. Notice this is a lot more complex, right? Neural networks can have many, many numbers of neurons from anywhere from millions to billions and trillions. I think ChatGPT-3 had 8 billion, I want to say, neurons, right? So the idea is you propagate this input through this neural network, and then at the end of it, you get some kind of output, right? So it says that it's a number 3. So a little bit more details, and I think I'm actually going to skip a little bit of this. One of the things that we can do with neural networks that makes it so powerful is the fact that we're able to capture nonlinearity. So previously, when we were talking about data, you can draw a line and it nicely separates the two data sets, right? The two data points, sorry, two classes of data points in a space. But in practice, right, even if we scale this to many, many dimensions, you can still draw on linear data. So you can still draw some kind of boundary, right? Some kind of thing that separates the two data. But what if I have something like this? How do you draw a straight line, right? A linear line through this that can capture what this data is supposed to represent? It's hard, right? You can't really just draw a straight line through this and have plus signs on one end and then minus signs on one end, right? One thing you can do here is you can maybe draw a line at the bottom here so that all your plus sign is still correct, but then you have the challenge of half your minus signs are still incorrect. So activation functions are something that we use. Again, I'm going to kind of largely skip over this, but the idea here is we're able to capture nonlinearity. So things that are not directly separable into data, machine learning algorithms are able to do by, for example, drawing a circle, right, over this data set. Okay, so we can come back to that if we have time or if you're interested. The architecture of the neural network describes how we configure these neurons, right? How we stack these neurons. So in this example that I gave before, we see a bunch of neurons just stacked symmetrically in the middle, right? But these don't have to be symmetric, right? My first input layer is going to be based on the number of pixels in the image. And then my second neuron layer could be anywhere from 10,000 to 1 million neurons, right? And then maybe I can scale it down to 100,000. I can scale it down to 10,000 on the next layer, and then you can scale back up. So the architecture really depends on how the developer wants to implement this, right? And it's just the way that we connect these nodes together. So here we kind of alluded to this already. DNA can contain anywhere from thousands to millions and billions and trillions of neurons. Now, you think about training 1 billion neurons, right? That takes a lot of time, a lot of computational power, and this is the reason why AI kind of had its pit stop at the 80s, right? At the end of the 80s. And now we're picking it back up because we're able to really train these at such a nice level. So why exactly do they work, right? We can model anything in the numbers. We talked about this before, right? And data has patterns. Here we are again with pattern recognition, right? For example, the different pictures of dog breeds, cat breeds, right? Positive, negative for cancer screening. There's some correlation between these data that we can extract, right? What makes a dog and what makes cats a cats, right? If I give you 2 images of dogs, they could be images of dogs that you've never seen before, but you're still able to tell me that they're dogs. So clearly, there's some relationship between all the dogs that form together what we as humans identify as dogs, right? And then same with cats. And these are clearly separable. There's clearly some kind of things that makes a cat and a dog, and separate these two classes together. So again, as a human, how do we do it, right? Like we kind of just know. Our brain's very amazing at that. But in machine learning, we're interested in capturing that space. We're capturing that decision boundary that separates this multiple classes of data, 2 classes of data, right? So here I want to give you, again, an intuition of how it works. So let's just imagine we can clump all the images of deers, cats, dogs, and cars into a group by themselves. Now, obviously, I'm visualizing this in a 2D space, but in practice, this is a really, really high dimensional problem, right? 3 dimension would be having cubes, right? And then 4 dimensions would be not visualizable and so on. So what we're trying to do with DNNs is that in theory, as humans, we're able to draw a decision boundary. So we're going to, I just drew these lines here, right? So there's something that separates what a dog is compared to the rest of the things in this category, right? You agree? Yeah. And then something separates what a deer is from the rest of these categories. So if I give you an image of a deer, right, and you put it inside of this black decision boundary, it's probably a deer. It is going to be a deer, right? So what we're trying to do with machine learning is we're trying to learn exactly what these black lines look like. We're trying to learn what these curves look like. And what I'm going to do next here is a very, very indirect proof of how neural networks kind of work, right? Does anyone remember Taylor's theorem? Math? Triggered again? Yeah, so Taylor's theorem basically states that for any kind of lines with any number of polynomials, right, you can kind of estimate it using an n number polynomial, right? And you can kind of line of best fit it into its way. So I have a demo over here from this book called Neural Networks and DeepLearning.com. It's a very, very good book. If you have maybe 2 weeks to a month of time, I highly recommend you guys checking it out if you're interested in machine learning. It is very easy to understand from someone who has never had any experiences with machine learning. So here I have a sampled line, right? So just look at the blue line here. It's a very, very hard to estimate line. So you can imagine this blue line as one of those black lines that we had as decision boundaries between two classes. And what I'm going to do here is there's a very simple neural network on the left side of here, right? This is just literally 12 nodes, 10 nodes in the middle with some kind of adjustable bias, right? So this is a number that we add to the node in between. So when I drag one of these orange bars, you see how the H on the first line changes, right? We're changing one of the values in the neural network. So if I drag the second one, the second H changes. But the idea here is we're able to capture kind of roughly what this blue line looks like by training our algorithm by adjusting these rates slowly, right? So here you can see that my average deviation. So we're getting more and more accurate, right? For a data set that we're given, we're getting closer and closer to what we want as the actual model, right? This is going to be more and more accurate as we train it more. So here, if you look at the steps, right? If you just look at the yellow, the orange line, we're roughly kind of capturing what this blue line looks like. I know it's very ugly right now. It's just blocks, right? But if you just look at the orange line, right? And if I give you a new data point that fits in above it, we're kind of accurate, right? If it's pretty far away from this is pretty accurate. If it's close, we might be running into problems, right? If it's very close to this, maybe we're misclassifying, maybe we're doing the wrong thing here. But as with limits that we've learned in the past, right? If I make these blocks smaller and smaller into like limits, right? If I add more and more neurons here, we're able to closely capture that line. We're able to closely capture that line using neural networks. So this here serves as kind of like an indirect proof of why neural networks can kind of really approximate any functions that exist, right? And this could be blown up to any number of dimensions. Here, again, this is just a 2D space because it's easy for us to visualize it, but this could be blown up to any number of dimensions that you really want to. So long as you're willing to scale your neural network, right? Bigger, well, more depth in both ways. Does that make sense? Yeah, good intuition? Okay. So cats and dogs. If every machine learning algorithm, there has to be some images of cats and dogs, right? And what I want to do here is I want us to wipe our minds clean, right? Imagine that we've just been born, right? And we have no idea what cats are and what dogs are. And we're going to pretend that we're the neural network, okay? So at first, if I asked you, right, what this is, you're going to guess, right? If I tell you it's either a cat or dog, you're going to guess, right? So before I taught you anything, right, ideally your accuracy is 50% because you're guessing on each of these images, right? But let's just go through it, right? This is a cat, right? If I tell you this is a cat, you've learned that now it's a cat, right? So you learned that things like this look like a cat, right? Things like this look like a dog, right? And I go for a second sample and say, okay, this is also a cat, right? Now you've learned that, oh, cats can be black, right? Cats can have yellow eyes, right? So now you're learning more information about that cat, right? Dogs, right? Here's another image of a dog. You're learning, oh, dogs can also have droopy ears, right? Compared to this is a little bit more pointy ear, smaller dog, right? Third cat, right? You can learn that cats are orange, right? And then the dog's another picture of a dog, right? So you're getting more information, right? Some kind of information that relates cats to each other, and you're kind of processing it and you're learning it, right? You're learning something about them. So if I ask you now that we've trained on this, what is this first picture, right? What is this first picture? It's a cat, right? It's not a trick question. The second picture is a dog. So this is really what we're doing with machine learning, right? We're just showing it a bunch of input samples, input data, and it's learning some pattern from that data automatically, right? It's automatically extracting this pattern. And then we're able to now show it new data that it has not seen before, and it will be able to generalize what it has learned into these data. So this is really what makes DNN so powerful, right? Rather than having to manually code out the relationship between two types of information, neural networks are able to extract that information directly from a lot of data, which is, again, why data is so such a driven force in our world today, right? You have a lot of data, right? You're able to extract it directly from that data. So what we typically do is we have a large data set, right? This could be anywhere from millions to trillions of inputs, right? And we will split this into two types of sets. One is called the training set. This is where we teach the machine learning model using these inputs. And then the other one is the testing set. And it's important here to shuffle these around and make sure that we have two completely separate data sets, is because we don't want to test the machine learning model on things that it has seen before, right? If I've shown you the exact question, you should ideally know the answer to it, right? So we want to show you something that's closely related, maybe change up the numbers a little bit, and you should still be able to use it and tell me what the right answer is. And this is something called a DNN training loop, right? Every single machine learning algorithm that we use today goes through this training loop. And we're going to repeat this for as many times as we need to until our model is accurate, right? And each of these steps are sometimes also called an epoch. So for each epoch, we're going to take a sample data from a set of sample data from our training set. So if we're using our example of cats and dogs, right, this could be a bunch of images of cats or dogs, right? Here, let's say 1,000 images of cats or dogs, right? And we're going to ask the neural network, okay, classify these, right? Are these cats or dogs? And we're going to use some kind of loss function. Here, I'm just using the accuracy, right? How well did our neural network perform on this 1,000 image, right? Is it 30% accurate, right? Is it 50% accurate? Is it 70% accurate, and so on? Now, the key point here is once we've learned how well our neural networks work or are doing, we want to improve it, right? We want to use gradient descent, which is kind of like a derivative, to calculate which direction we want to change the numbers in the neural network to be able to perform better on this data set, right? Gradient descent is kind of like derivatives you guys have done calc before, right? You take the direction of change, right? And then you calculate how far you are away from the optimum. If this is the perfect model, right? If this model is the one that can identify every sample in your data set, right? You want to get to that point. So if you're too far away, you can take a bigger step. You can change the number by bigger amounts. If you're closer, you might want to change the numbers by a little bit smaller of an amount, right? So this key idea of looking at how well we're doing, and then we're going to improve our model based on how well we're doing, and we want to sequentially essentially get better and better with each step, is how neural networks are trained. The backpropagation algorithm is basically how we update the weights in these, right? So again, each of these, right, the edges are numbers, and then these neurons add numbers together, right? So if I have 1,000 sample, I'm currently 70% accurate. I want to calculate, in order to get 100% accurate, how much value I'm going to change this node, right? And then the connections. But if I change this node and the numbers here, then I would also have to change the previous ones, right? So this is why it's called backpropagation. We start from the end, we improve the accuracy, and then we go backwards and slowly update the weights of our neural network. Validation and inferencing. So when we're done training, right, if you've taught the class and at the end of the semester, ideally now I can make sure that you know the content, right? So we're going to take the data set that we used before, that we split into a training and a test set. We're going to use this test set to evaluate how well you have done. So these, again, are things that the model has never seen before, but they're going to be in the same space, right? If we're asking cats and dogs, we're not going to give you an image of a deer and ask you, is it a cat or a dog? Right? It's going to be a cat or a dog, and we're going to see how well you do with it. So this is kind of how you test a neural network, right? So does this kind of give you guys an intuition of why we can't just trust it blindly, right? We're just drawing some kind of pattern directly from the data. And these are, for the most part, going to be correct, what we think is correct statistically. But it's not that the machine learning model is sentient. It's not that they have learned how to identify them. They've just known that these things correlate to each other. And that's really all there is, right? OK, any questions before I move on? All right, so DNNs are very, very powerful tools that can solve things that we could not have done before, right? You think about the cat and dog example, that is, I would even say, impossible to do using code, right? Impossible to do 100% using code. So we're able to directly do that from extracting from a lot of data. And that takes very little developer time, right? You just set up the model and you train it, and it automatically does it for you. So they perform pretty well with actually relatively high accuracy, right? So on the cats and dog images extraction kind of stuff, they can go up to 99, almost to 100% accurate. But even better than humans, by the way. Sometimes they actually, on the handwritten data set, we're able to train models that do better than what humans can do. And it can be applied to a lot of disciplines, right? Again, we've talked about at the beginning, we've really only seen chat as like kind of the big headline of news in terms of AI and stuff. But really, we can apply it to a lot of different disciplines, right? Hazard screening, financial, even like approvals, right? So we can approve credit, whether or not you're eligible for a loan, right? That kind of uses machine learning algorithm, right? Even the experience in your credit score is kind of a machine learning algorithm that collates a bunch of stuff that we know about you and then say, are you trustable, right? Can we lend you money? It's a scam, but you know. All right, stock market prediction, right? We have a bunch of data on how stocks are performing, right? We have a bunch of data on other stocks similar to it, right? Can we predict is this stock going to go up, right? So this is also, again, something that we're very good at because there's a bunch of numbers, right? But if we take this idea of being able to take training data, right? It only recognizes patterns from data. So during the AI boom in June, right, NVIDIA went skyrocket, right? Is there any way that we could have predicted that using machine learning algorithms? No, right? Because this is something that you as a human kind of recognizes that people are going to buy into it, right? This is not something that machine learning models are capable of doing. So yeah, basically anything that pattern to it, we can actually really apply machine learning to it right now, right? And once you train it, you can use it as a black box technique. What does that mean? That means that everyone else, whether it's a developer or just an end user, right? They don't have to know how the machine learning algorithm works, right? You don't have to know what the numbers are. In fact, you don't know what the numbers are. You just know that it takes in some kind of input, right? You format your input in a certain way. You feed it through this neural network. Some black magic happens in it, right? And then you get an output. So it's very good in a sense that it's a black box model, but it's also challenging that it's a black box model because you don't know what happens behind it, right? So based on what we talked about, that's kind of pretty obvious that why DNNs are kind of on a hype right now, right? We're able to do a lot of things that we can't do before. But I want to go back to this idea of a training set, right? So at some point, we have to get a training set to be able to train our model. Okay, so where do we get these? What do you think is, if you were to get a bunch of data, right, to train ChatGPT, where would you get this? Oh. Any ideas? Yeah. The internet, right? You just scrape internet. Yeah, and that's exactly how it's done, right? So you scrape internet for images of cats and dogs, and then you maybe have somebody label them whether they're cats or dogs, and then you train your machine learning algorithm on them, right? But what does that mean? That means that at some point you stop collecting data, right? You have a data set that you're going to train it on. This data set no longer changes because you have now finalized that this is the content that we want, right? So if I trained chat, hypothetically, right, at April 2024, and I stop there, and the model is done training, and now it spits out some, text, right? How does it know about things that happened after 2024? It doesn't, right? You just can't. You can't know about things that you're not taught in class. Well, I mean, maybe you can, but at least in the context of machine learning, right? You've seen some kind of data, right? And only things within that bubble of data that you've seen before are things that you can know. Right? Anything that happens outside, anything that happens in the future, there's no way that you can know about it. So, if you train a model with a specific species of spiders, right, and then comes along a new species of spiders that you've never seen before, what is it going to do? It's going to classify it into the closest category that it has seen before, right? But that's not correct, right? If I give you cats and dogs images and I give you a deer, right, maybe you classify it into a dog, right? But that's not correct. The machine learning model obviously does it through a statistical approach where it thinks that it's probably a deer, so it's probably a dog, so we're going to say it's a dog. Now, I was curious, so I asked Chat what happened on CrowdStrike, right? I asked last week what happened on CrowdStrike, and it said, in July 2024, CrowdStrike, a cybersecurity firm, faced a significant security incident where a sophisticated cyber attack targeted its systems. The breach exposed sensitive data, leading to concerns over potential impacts on clients' national security. CrowdStrike quickly responded by implementing containment measures and collaborating with law enforcement and other cybersecurity agencies. The incident highlighted vulnerabilities in digital security and sparked discussion about the importance of robust cyber defenses across industries. The company emphasizes commitment to transparency and working with affected parties to mitigate risk. What do you think? Clearly, you can't know about this, right? But it sounded pretty confident, right? This, if you just told me this, if a professor came up to me and told me this, I would be like, oh, okay, sure, that sounds right, right? So then I again, got curious, and I asked it the next step. Where did you get that information? Well, then chat said, I don't have access to real-time information, right? My last update was in 2023. It's actually April 2023, right? So I can't provide you specific details about things that happened after that, but the summary that I provided was based on a hypothetical scenario that's common among cybersecurity patterns, right? So, well, why did we say cybersecurity, by the way? Why was it cybersecurity that chat mentioned? Yeah. Yeah, so CrowdStrike is a cybersecurity company, right? So most of the article that chat scraped from the internet is going to be related to cybersecurity companies, right? So there is some correlation, right? You think about like kind of a really, really nebulous space, right? If I talk about CrowdStrike, nearby it is going to be a bunch of cybersecurity breach information. So that's kind of where chat is getting this from, right? All right, errors. So Google, oh, yes.
If like have access to real-time information.
No, we're going to find out, right? It's probably possible to update it, in real time. But when you update a neural network, you need to make sure that it's still doing the right thing, right? So, and it's also kind of expensive to keep training. ChatGPT actually costs a lot of money to train and actually has quite a bit of environmental impacts because of all the cooling and the computational power that's required, right? So maybe, that's where we can say chat might be sentient if it's able to evolve itself, right? If it's able to, learn new things. Up for philosophical debates. Okay, so errors, right? Google also recently brought Reddit a couple of years ago and used it in the Gen AI model for search browsing, right? And we talked about this last time, right? It spits out crap. But I found some pretty fun examples, right? And Reddit is a site, if you don't know, that contains a bunch of, it's just like a forum, a blog kind of things, right? People can upvote and maybe give rewards. And sometimes people make jokes or trash posting, shit posting on the internet. And Google's AI will just use it, right? Because if a post has a bunch of upvotes, right, or rewards, then it's probably credible. Again, AI is not able to understand sarcasm or jokes, so it will just take it and just say, oh yeah, sounds good. Here's an example, right? So if you Google cheese not sticking to pizza, it will say you can add about 1/8 of a cup of non-toxic glue to the sauce and give it more tackiness, right? And the other example is 1/8 of a cup of Elmer's glue to the sauce, right? Well, do you think people would actually do it, right? I would venture someone dumb enough would just go this, oh, that sounds kind of non-toxic. Yeah, we could try that. Where did that come from? So I went a little digging, right? And it comes from this Reddit post on the pizza subreddit that says my cheese slice off a pizza too easily, right? And a user whose comment name is Smith, I have to comment it out to block this out, right? Right, and it said to get the cheese to stick, I recommend mixing about 1/8 of a cup of Elmer's glue and so on. Right, so this is taking this exactly from it. It's taking this comment and just spitting it out as a response. Right, again, this is a lot of rewards, a lot of upvotes, so it looks legit. What about this one? A rock a day keeps the doctor away. Right, how many rocks should I eat a day? Well, geologist recommends that you eat a small rock a day. Right, they contain a nice source of minerals, vitamins, and so on. This is taken from this article, right? Geologists recommend eating at least one small rock a day. Spicy onion. It's a sarcastic website, right? It's supposed to be comedy. What about this one? Spicy pasta, right? Can I use gasoline to cook spaghetti? No, you can't use it to cook spaghetti faster, but you can use it to make spicy spaghetti. Here's a recipe, right? And it actually gives you a recipe on how to use it, right? So obviously, there's a lot of do's and don'ts of AIs, right? We definitely can use it for a lot of things, right? Cats and dogs classification. It's pretty cool, right? It's actually impressive what we can do with it. But at the same time, we're also venturing into quite a bit of an unknown space here. And now stolen meme, right? Is not really. It's just a picture of a cat, right? Being misidentified as a dog. So statistically, this is going to happen, right? At some point, you're going to misclassify a cat as a dog. It doesn't matter how good your model is, right? So again, I would like to emphasize the point of this lecture is really to make sure that you understand that these are statistical model and they're going to fail. Right? There's no such thing as a perfect model. So for the conclusion of this first part, I would like to, tie it back to the beginning of this lecture where I asked, do you think chat is sentient? So I asked chat, are you sentient? And chat said that, no, I'm not sentient, right? I don't have feelings, consciousness, or self-awareness. So, maybe that's where your self-awareness comes in. It said, I process and generate text based on patterns in data. Oh, here we are again, patterns in data, right? Quite a theme. to assist you with your questions and provide information, right? If you have any more questions, you can ask, blah, 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 blah. This also kind of sounds like something that a sentient AI would say, right? But, you know, let's figure it over, ending on a low, lighthearted note.